So we're going to start this second video taking a look at higher order bonds, and by that I mean double and triple bonds. And so you can see from your organizer that a double bond is really a situation where instead of just one pair of electron, two pairs of electrons are shared between the same two atoms. And a triple bond is when you have three pairs of atoms shared between the same two atoms. It is physically impossible to get all four orbitals close enough to share four bonds, so there is no such thing as a quadruple bond. The highest we go is a triple bond. So let's do a couple of examples of this rule number 5. So gonna start off again very simple. What if we want to draw the structure for oxygen, diatomic oxygen? What's that formula going to look like? Well, if you think about it, each oxygen has 6 electrons. So in order for each oxygen to get 8 electrons, they can't just share that one bond. That's not enough because there's an unpaired electron on each of them. So if they share that second pair, now you get a double bond. So typically when we draw a double bond, we draw essentially an equal sign, so 0 equals 0. But that's an example of a double bond. You're sharing 2 pairs of electrons. Likewise, I can show you 3 pairs of electrons being shared if I do diatomic nitrogen. So nitrogen has just 5 electrons. So again, I'm going to write those dots so that the unpaired electrons are oriented towards each other, and then you can kind of see there's 1 bond, there's 2 bonds, and there's 3 bonds. So again, to show a normal triple bond in a Lewis structure, we do something like that, 3 lines. So this is kind of a work in progress thing. When you want to do the final drawing, this is what you want it to look like. And again, structural formula-wise, we're just going to drop the non-bonding pairs of electrons. So we're going to make it look something like that. So let's take a look at something a little more challenging. How about PSF? All right, what's the formula for PSF going to be? Well, phosphorus, like nitrogen, has 5 electrons. Sulfur, like oxygen, has 6 electrons. Fluorine has 7. So if we think about our rules, what's going to happen? We're going to put the atom that needs the most bonds in the center. So that's going to be our phosphorus. So fluorine makes sense. I can put 1 bond to fluorine, and then I can put another bond to sulfur. But sulfur and phosphorus still aren't satisfied because they each have that 1 unpaired bond. So what do I need to do? I need to draw a second bond. So what's the Lewis structure going to look like? Fluorine single bonded to phosphorus, and then sulfur double bonded to phosphorus. So there's my Lewis structure for PSF. How about C2H4? Okay, so I got 2 carbons. Each carbon needs 4 bonds. So you know that I'm going to have 2 carbons in the center. Okay, so I do carbon, carbon. I can put 1 bond there. Okay, now I got 4 hydrogens. So if I put 3 hydrogens here and 1 here, this carbon is lacking 2 bonds. That one doesn't make too much sense. So I want to try and keep things as symmetrical as possible. So since I have 4 hydrogens and I need 6 bonds, hopefully instinct says, well, you're going to have to form another bond between the carbons. And that's what I'm going to have to do. So I form another bond. Now, look, I got spaces for the 4 hydrogens. And it looks a little bit more symmetrical than putting 3 on one side and 1 on the other. So there's an example of a double bond between 2 carbon atoms. I can have a triple bond between 2 carbon atoms as well. If I do C2H2, now I only have 2 hydrogens to work with. So not only do I need a single bond between carbon, I only have 2 hydrogens. So 1 hydrogen there, 1 hydrogen there. I got to form a double and then a triple bond. So hydrogen on the two ends, triple bonded carbon in the center. Notice that the Lewis structure for all of these things with carbons and hydrogens is exactly the same as the structural formula. There's no valence electrons that are unpaired. That's going to come into play a lot as we move into organic stuff. All right, are you getting the feel for what to do with a double and a triple bond? You've got a problem set to work on for those. But I think since we're only 5 minutes into this video, I'm going to go on and do the next topic, or the next rule, and that is what happens when we deal with ions. So with ions, we're going to have either extra electrons or we're going to be short electrons that we need to use in order to fulfill our octet. So things are going to start to get a little wonky here. You got to really just kind of sit back and think practically about how the bonding scheme should happen, okay? So let's start off a little bit easier. One of the ones I like to do, let's do cations. NO plus is a cation that you don't have to know, but it works as a way for us to understand. So if you think about it, nitrogen has 5 bonds, or 5 electrons. Oxygen has the 6. But I've got to be short one. So I have 5 plus 6. So 11 is what I'm normally supposed to have. That's not an H. 11 is what I'm normally supposed to have. But since it's a plus, it's minus 1 electron. So I really only have 10 electrons to work with. So I got to remember to deal with that somehow. Okay, so nitrogen and oxygen, I'm going to obviously put the lone electrons kind of near each other. So you can see 1 bond here, 1 bond here. Well, in order to lose an electron, what's going to have to happen? I can take this electron away, or I can break up this pair and take one of those electrons away. Either way, at this point, I'm going to mark either one of them acceptable. So if you do that, but to show that it is a charge of plus, I'm going to put it in brackets. Or if you do this, I'm going to mark that acceptable as well. Now, if you think about it, which one makes the most sense in terms of filling the octet rule? This one fulfills the octet rule. This one kind of is not really fulfilling the octet rule appropriately. So this one is the one that makes the most sense. So even though oxygen isn't supposed to form 3 bonds, it does here. This one makes oxygen okay, but now it knocks nitrogen out of whack. So one of these atoms is going to look weird because of the fact that we've lost an electron. Sorry, there's my phone. So that's the case for ions. You are going to have kind of weird looking structures. So if it's a cation, you're going to remove an electron, right? There's not a whole lot of cations to work with. I know we have ammonia. I don't want to do that quite yet because that takes into account the last rule that we need to look at. So if you're doing a cation, remove electrons. And you always want to try and keep pairs. You want to try and keep the octet. So this is the one that makes the most sense, even though oxygen isn't really supposed to have 3 bonds. This one, I would not mark wrong based upon what you know. So either way, so if you take this lone electron away, or if you break up this pair, because typically we don't break up pairs, so don't break up that pair, but just remove that 1 electron. All right, so those are cations. Let me get another sheet. We'll take a look at anions. There's obviously many more anions that you have to work with. So let's start off with something simple like ClO minus. Okay, so again, oxygen needs 6, or oxygen has 6, chlorine has 7, but this minus means I have an extra electron. So I have 6 plus 7 is 13. I have 14 electrons to work with now, technically. All right, so hopefully it makes sense that I'm going to stick a bond between oxygen and chlorine, okay? But now chlorine is satisfied, 2, 4, 6, 8, but oxygen is not. But don't forget I have this extra electron to work with. So where's that extra electron going to go? It's going to go right there. Do I need to mark it different? No, but I just wanted to do it for you guys. So the Lewis structure for ClO minus looks something like that. And remember, it's an ion, so we're going to still kind of put it in brackets and give it a negative charge. Okay. How about if we do NO2 minus nitrite? NO2 minus. Okay, so nitrogen has the 5 electrons. Each oxygen has 6. So I know I need at least one bond to each oxygen. Okay, but now I've got this situation. I've got 3 electrons. But wait, I have 4 electrons that need pairing up. Well, if I do a double bond here, that takes care of oxygen and nitrogen, but this oxygen is still short, but I've got that extra electron. So if I put that extra electron there, there's the extra electron. Now I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. The atoms are all satisfied. The octet rule is fulfilled. So how would I draw it? I've got a double bond to one nitrogen, a single bond to one oxygen, a single bond to the other oxygen. And then I have this extra pair of electrons around this oxygen because of that extra electron that gives it the charge. Okay, so ions are a little bit harder. Some of you will click on it right away, some of you won't. But it just takes some practice. So how about give it a shot, try PO3 minus 3. What's going to happen there? So why don't you pause this and give this one a shot, see what you come up with. All right, so phosphorus needs the most bonds. That's going to go in the center. I got 3 oxygens. I got 3 dots for phosphorus to need a bond. So I can put 1 oxygen at each phosphorus. Okay, but then I have these 3 lone ones. But I also have this charge of 3 minus. So I can put 1 electron there, 1 electron there, 1 electron there. Put it in brackets. That's an ugly bracket. Put it in brackets, show minus 3. That way I don't have to actually make an X. I can just put a dot to let them know that there's an extra charge. So P, O, O, O would be actually the structural formula if I don't show any of the dots. Okay, so again, you've got another problem set that lets you practice ions. So go ahead and give that one a shot. I'm going to stop this video. We've got one more situation that we got to take a look at. So we've got to go on to video 3 on coordinate covalent bonds. That's the one that's probably going to blow your mind a little bit.